So, with that example, you have seen a concrete illustration of Bootstrap. Because in each replication, we are drawing with replacement a sample of size n from the original sample of size n. It's very possible that we will end up with some repeating observations that are drawn more than once. Well, why does a statistic TB calculated based on these resampled values? Why does its empirical distribution approximate the sampling distribution of T we are interested in? Here, I will provide an intuitive explanation instead of a thorough proof. The idea centers around something called empirical CDF, or empirical distribution function. To understand the rationale behind Bootstrap, we first need to recognize the relationship between the theoretical CDF of the random variable x, which we denoted by fx, and the empirical distribution function, or the empirical CDF, of a random sample x1, x2, all the way up to xn. The theoretical CDF, ff of small x, is by definition the probability that a random variable x is less than or equal to small x. We know that the CDF characterizes the distribution of the random variable. If we know the CDF, we know its distribution. In this case, in the scenario of Bootstrap, we are faced with the situation where we often do not know what exactly is fx. On the other hand, the empirical distribution function, empirical CDF, is defined as follows. Given a random sample, x1, x2, all the way up to xn from fx, the empirical CDF is given by fn of x, small x, which is equal to the sample mean of the indicator function that xi is less than or equal to small x across a total of n random samples. Intuitively, this tells us the proportion of the random samples that are less than or equal to a particular constant small x. What you can see from here is that fn of x, the empirical CDF, is an unbiased estimator for fx of x. So it's a sample mean. You can see that its expectation is equal to the expectation of the indicator function here, where the expectation of the indicator function is just the probability. Px is less than or equal to x. And that's fx. So fn of x is an unbiased estimator for fx when we give it any particular constant x. In addition, given observed samples x1 all the way up to xn, fn of x is itself also a CDF. And that's actually the CDF of the discrete random variable that's uniformly distributed on the set x1 all the way up to xn. So you can see that here, when we draw our bootstrap samples, x1 of b, x2 of b, all the way up to xn of b, independently with replacement from this set, what essentially we are doing is we are drawing random samples from Fn, the empirical CDF. In other words, our bootstrap samples are essentially random samples from Fn. So how does this relate to what we are trying to do, which is showing that the empirical distribution of TB actually approximates the sampling distribution of T we are interested in? Well, we have to learn something about the asymptotic properties of the empirical distribution function. Note that for any constant that is a real number, small x, fn of x, which is equal to the sample mean of the indicators, so our empirical CDF, is the sample mean of the indicator function evaluated at xi less than or equal to constant x. And we can see that the expectation for this E of indicator xi less than or equal to x is equal to the probability that xi is less than or equal to x, and that's fx of x. So this is a sample mean of IID samples, of a function of IID samples. And as n goes to infinity, so as our sample size gets larger and larger, by the weak law of large numbers, we know that this sample mean fn of x converges in probability to fx of x for all possible x values in R. So what this says is that as n goes to infinity, the empirical CDF will get closer and closer to the theoretical CDF for x. You might not have learned strong law of large numbers in 410, but if you have taken 510, you might know that by the strong law of large numbers, we can get even stronger result. We can show that fn of x, which is the empirical CDF, converges almost surely to fx of x, the theoretical CDF for x. There's actually an even stronger result. If you take courses like probability theory or large sample theory, you might be introduced this result. So this is known as the Golikov-Cantelli theorem. So what this says is that as n goes to infinity, the supremum out of all possible x's in R of the distance between the empirical CDF evaluated at x and the theoretical CDF evaluated at x will converge to 0 almost surely. So this thing is sometimes known as the Kolmogorov-Smirnov distance, which you might encounter if you learn about hypothesis testing for whether two distributions are equal. So what essentially all of these say is that as our sample size gets larger, our empirical CDF will get closer and closer to the theoretical CDF, which we don't know. So what does this mean for bootstrapping? Intuitively, for a sufficiently large sample size n, fn, which is the empirical distribution function of our random samples, will be close to fx. If we sample x1 all the way up to xn repeatedly from fx, and then compute t, which is the function t evaluated at x1 all the way up to xn, we are essentially drawing from the sampling distribution of t. This is what we did last time with Monte Carlo inference, where we sample from fx, the distribution we know, so the theoretical distribution of our x's. We compute t based on our random samples from x, and we know that the distribution of t we will end up with across a large number of replications will approximate the sampling distribution of t. On the other hand, in Bootstrap, instead of sampling from fx, the x1 up to xn's, we are resampling x1b all the way up to xnb in each Bootstrap replication repeatedly from fn, not fx, but the empirical CDF. And we compute our tb, which is evaluated at x1 of b all the way up to xn of b, which are resamples from the empirical distribution. So you can see that the only difference between Bootstrap and Monte Carlo inference is whether we draw the x's from the theoretical distribution fx or from the empirical distribution fn. If fn and fx are close, then the theoretical distribution of tb should also be close to the sampling distribution or the theoretical distribution of t. And we know that for large n, fn and fx are supposed to be close. In addition, for a large enough b, The empirical distribution of the TBs, which are the T's across the total of B replicates, will also converge to the theoretical distribution for TB. In other words, if our sample size is sufficiently large, so if our n is sufficiently large, then Fn and Fx are going to be close, meaning that the theoretical distribution of TB is going to be close to the theoretical distribution of T, which is the thing we're interested in. And if we do a sufficiently large number of bootstrap replications, then the empirical distribution of the TBs, which are the actual draws that we obtain, will also be close to the theoretical distribution of TB, which is close to the sampling distribution of T. This is why the empirical distribution of TBs we obtain using Bootstrap can be close or can approximate the sampling distribution of T, which is the thing we're interested in.